Hey guys, today we're going to be talking about absolute value functions. In the past, we've already discussed the fact that absolute value functions are V-shaped graphs centered at the origin, 0, 0, and containing points where y is equal to x on the left and the right side. So on the right side, we have the point over 1, up 1, over 2, up 2, over 3, up 3, etc. On the left side, we have a negative slope. So if I go left 1, I go up 1. So I've got negative 1, 1, negative 2, 2, and so on. So when we look at this absolute value function, we can also think back to our transformation form of a function, and we realize that we can express this as f of x is equal to a times the absolute value of x minus h plus k. In this case, h comma k is the vertex of the V. K is our vertical shift parameter. It slides that vertex and all the other points up and down. H is our horizontal shift parameter, which slides our vertex to the left or right. It actually slides the entire V to the left or to the right. And A is the slope of the lines that form the V. On the right side, we'll have the positive slope, and on the left side, we'll have the negative slope. And if A is negative, that means it's flipped upside down. So let's go ahead and apply these principles to some examples. Say that I wanted to graph the function f of x equals 2 times the absolute value of x minus 1 minus 3. In that case, the first thing I want to do is identify the value of a, h, and k. Here we have a is equal to 2, h is equal to 1 because we have x minus h in our formula, and k is equal to negative 3. That means we're going to take our original graph of f of x, our V-shaped graph, and we are going to shift it down 3 units, right 1 unit, and we're going to make the slope on the right positive 2 and the slope on the left negative 2. So I'm going to go ahead and plot the original graph of absolute value of x. Here we have our center at 0, 0. And I'm just going to plot the point over 3, up 3, and left 3, up 3, so that I can get my shape here. I don't like that line. Let's try again. That's a little bit better. So what I'm going to do is take each of these points, and I'm going to move them right 1 and down 3. I'll start with the vertex. So I'm going to take my vertex and I'm going to go right 1, and then I'm going to go down 3 units. So my new vertex is going to be located at the point over 1, down 3, which makes sense because h is 1 and k is 3, and that tells us our vertex is 1 comma negative 3. Then, instead of shifting my other points, I'm going to locate the position of new points using the slope of 2. So when I say that my slope is positive 2, I'm talking about the slope for the segment that's on the right side of the vertex. So I'm going to go, my change in y is 2, my change in x is 1. So I'm going to go right 1 and up 2. And I'll do a few of those, right 1, up 2, right 1, up 2, right 1, up 2, and so on, so that I'm able to get this shape here. And on the left, I'm going to do the opposite. I'll go left 1 and up 2, left 1, up 2, left 1, up 2, and so on. So I complete my symmetric V. I'd like to complete it really nicely. But sometimes that doesn't, whoops, sometimes that's not in the cards. I think I can do it though. There we go. So If the black graph is the graph of y equals absolute value of x, the blue graph is the graph of f of x equals 2 times absolute value of x minus 1 minus 3. So in the event that I wanted to write the equation for the function represented by this graph, I'm going to work in the opposite order of what I just did on this previous slide. On the previous slide, I looked at the equation, identified a, h, and k, and then used that to graph the new graph. On the other hand, in this one, I'm going to look at the graph and determine a, h, and k. Then I'm going to use it to write the function. So our function form is f of x equals a times the absolute value of x minus h plus k. Our vertex is at h comma k. And if you look on this graph, the vertex is located at the point 0 comma negative 5. X is 0, y is negative 5. So that means my vertex is equal to 0 comma negative 5. And it also tells me that h is equal to 0 and k is equal to negative 5. So the only thing I need to figure out is a, which is the slope of the segment that's on the right side of the vertex. So I'm going to find two perfect whole number coordinate points. I'll choose the point 2, negative 3 and the point 4, negative 1, because I just have a little bit of space to write there. That's all. Any 2 points would do. Here, my change in y is positive 2, and my change in x is positive 2. A is equal to change in y over change in x on the right side of my vertex, which is equal to 2 over 2, which is positive 1. So that tells me a is equal to 1. So my function is f of x equals 1 times the absolute value of x minus 0 plus negative 5. Simplifying that, we get f of x equals absolute value of x minus 5. And here we can see that even if you just plug in exactly what a, h, and k are, you're not going to get an equation that Lewin's going to recognize as correct until you simplify it. Also, if our x-coordinate of the vertex is 0, that means we have no shift to the right or left from the absolute value of x. That's why we just have absolute value of x in our function. In this example, we're going to use the same patterns that we just observed in the function form of an absolute value equation, f of x equals a times x minus h plus k. And I'm going to identify a, h, and k, although if you notice, just looking here at the beginning of each function, none of them have a multiplier, so I don't actually have to worry about a. So I'm going to identify h and k from each of these functions, and that's going to tell me the coordinates of the vertex. So in this case, in part A, h is equal to minus 9. H is equal to positive 9, but I do x minus 9 because it's x minus h. H is positive 9, and I have nothing being added on the outside of my absolute value bars, so k is equal to 0. In my second equation, I'm not going to be able to ignore that that's not the same color. All right, in my second equation, k is positive 9, because that's the number being added on the outside of my absolute value. But inside of the absolute value with x, I have x minus nothing. So that means h is equal to 0. For part C, I have h is equal to 9 and k is equal to 0. And that's not quite right. H is equal to negative 9. Remember that x plus 9 is the same as saying x minus negative 9. And what we want to know, h is what's subtracted from x. Negative 9 is being subtracted from x. But my k is equal to 0. And last but not least, in part D, h is equal to 0 and k is equal to -9. So now all we have to do is look at these vertices that are labeled 1 through 4 on the right and match them up. So part C is this vertex of -9, 0. Part A is the vertex of 9, 0. H comma k is 9, 0. 0, -9 is graph D. And then for the fourth one, we have only one that hasn't been matched. That is B. So in that case, we have the vertex of 0, 9. Now we're going to talk about solving absolute value equations and absolute value inequalities. And I want to start by just giving a little bit of background information about what the absolute value means. Absolute value is the positive distance between a number and a reference point h. So when I say the absolute value of x minus h, I'm referring to the distance between x and h. So when I say absolute value of -3, I'm looking at the distance between -3 and 0. It's just as if I had the absolute value of -3 minus 0. In that case, I'm going to look over here at 0, and I'm going to look over here at -3, and I can tell that the distance between them is 3 units. So the absolute value of -3 is equal to 3. Now, if I start at 0 and go to -3, I'm going 3 units in the left direction. And if I start at -3 and go to 0, I'm going 3 units in the right direction. However, it doesn't matter which direction you travel if you are only reporting the distance, because distance is what's called a scalar quantity. That means that it has only size and it does not have direction. So in this case, the absolute value of -3 is equal to +3 because the distance is 3 units from 0. Similarly, if I want to find the absolute value of 5, I'm just asking how many units away from 0 is the number 5. Here's 0. I'm just going to arbitrarily place it here. And I can go to the right 1, 2, 3, 4, 5 units to get to 5. The distance is equal to 5 units. So the absolute value of 5 is 5. Similarly, if I say that the absolute value of x is the distance between x and 0, then what we get is the positive output. So it's x without the sign. So we don't always have, like in all the previous examples, our reference point was 0. We were looking at the distance between a number and 0 in each example. In this example, our reference point is 2. So we say the distance between x and the number 2 is 3 units. Whenever you are reading an equation like this, you would say the word is when you get to equals. So when I see the absolute value, I call it the distance. Is 3 units. This is helpful as we get into more complicated examples. So between x and 2, so I'm going to come over here to the number 2. Here's our reference point. The distance between x and 2 is 3 units. I could go right 3 units to get to 3, 4, 5. Or I could go left 3 units, which would take me to -1. So the absolute value of x minus 2 equals 3 tells us that x is equal to either -1 or 5. And there are 2 solutions, because when I don't know my number, I only know the distance. I can go to the right or to the left, that +3 units. Now, in the event that these get more complicated, they're not always easy to show on a number line. The logic always works, but sometimes they get more complicated to think about. So I want to talk about this while it's nice and simple, just to give an algebraic strategy for solving absolute value inequalities. Notice that if I say there are two numbers that have an absolute value of 3. We have the absolute value of -3 is equal to 3, and we have the absolute value of +3 is equal to 3. This tells us that the number inside my absolute value, that is x minus 2, is either equal to -3 or to +3. So I'm going to write and solve an equation for each case. On the left, I'll solve the equation x minus 2 is equal to -3. Keep in mind this -3 isn't a negative distance, it's the number inside the absolute value, and that's okay. On the other hand, I'm going to solve the equation x minus 2 is equal to +3. Again, this positive and -3 refers to the number inside my absolute value bars that has an answer of +3 as the distance. So now I'm just going to solve this equation. I will add 2 to both sides of the equal sign. And since my equations are set up sort of identically, I think it's kind of fun to go through and double solve. Whoops. When I do this, I get x is equal to -1 or x is equal to 5. Notice it's the exact same solution that we got when we did the number line approach. That's right, another example. If I have an equation that says the absolute value of x plus 5 is equal to -1, that means the distance between x and the number -5 is -1 units. This is not possible because the distance is always positive. That means the solution is D and E. Because I cannot have the absolute value equaling a negative number. The distance, when I have an absolute value expression isolated, there's nothing else happening to it, the answer cannot be equal to a negative number. So we can go ahead and apply these lessons to solve these two examples. On the left, we have the absolute value of 3x minus 1 minus 10 is equal to 0. The first thing we want to do is isolate these absolute value bars to make sure that we are able to write two different equations that represent the distance. I'll start by adding 10 to both sides of the equal sign. When I do that, I get the absolute value of 3x minus 1 is equal to 10. So the distance between 3x and 1 is 10. So that means there are two possible solutions. Either I can have the absolute value of -10 equals 10, or I can have the absolute value of +10 is equal to 10. So I'm going to write two equations, one where 3x minus 1 is equal to -10. And again, that is this -10. It's not a -10 on the outside. On the other hand, with this other +10, I get the equation 3x minus 1 equals +10. So I'm going to go ahead and solve. I'll add 1 to both sides of the equal sign on each equation. Leaving me with 3x equals -9, or 3x equals 11. My last step to solve these equations is to divide both sides of the equal sign by 3 on the left equation and on the right equation. My solutions, therefore, are x equals -3 or x equals 11/3. For the example on the right, I want you to take a moment and try to see if you can work through that problem before I step in. Go ahead and pause the video and work it out. Resume the video when you're ready to see the answer. All right, my first step here is to isolate my absolute value expression. So I'm going to subtract 9 from both sides of the equal sign. On the left side, I'm left with negative absolute value of 2x plus 5 is equal to 4. Now I still am not isolated. I need to have a positive absolute value by itself on one side of the equal sign. So I am going to divide both sides of the equal sign by -1. On the left, I get 2x plus 5. And on the right, I get -4. This tells us that there's no solution. I know this because absolute value is always positive. Excuse me. It's important to note that if you just went ahead and split the equation into two separate little equations, making 2x plus 5 equal to +4 and 2x plus 5 equal to -4, you would get two answers, but you would be solving the problem absolute value of 2x plus 5 is equal to +4, not negative, because there is no number you can put inside the absolute value that a -4 comes out of. We solve absolute value inequalities in a very similar way to the way we solve absolute value equations. First of all, I don't know how this happened, but I'm just going to white out this weird Star Wars looking lettering and give myself some room to work. So if I say that the absolute value of x minus 3 is more than 2, think of this on a number line. The distance between the number 3 and x is more than 2 units away. Exactly 2 units away takes us to 5 and 1. So what I want to do is shade my number line to recognize all of the points that are more than 2 units away from 3. So all of these points here, this tells us that I have a solution that is a set of intervals. That's how I'm going to write my answers. I have that x, oops, on the left, I have that x is less than +1, or on the right, I have x is greater than 5. In interval notation, that looks like this. I go from -infinity all the way up to 1. And I combine that interval with the interval from 5 to +infinity. The number line and the inequality are just a tool to be able to write the interval notation. You have to be careful when we're talking about having a negative on the opposite side of the inequality symbol from an absolute value. Rather than always equaling does not exist, you need to interpret the results based on what the inequality is saying. Here, in this first example, we're saying the distance is less than -1. This does not exist because -1 is already negative, and anything smaller than -1 will still be negative, and we cannot have a negative distance. But look at what happens in this bottom example. This example says that the absolute value, or the distance, the absolute value, is more than, well, is greater than or equal to -1. This is always true. This is always true because we know the distance is positive, and every positive number is larger than -1. So any number can work for x because any number that I choose is going to result in an absolute value that is larger than -1 because it's going to result in a positive number. So in this case, x is equal to infinity, or we would say that the solution is from -infinity to +infinity. All real numbers are solutions. So here's how we approach solving absolute value inequalities. We are going to make sure that we have isolated the absolute value bars on one side of the inequality symbol, and everything else is on the right side of the inequality, or the other side of the inequality symbol, and it's simplified. Then I'm going to solve an equation to identify the dividing points that break up our number line into solutions or non-solutions. And I'm going to shade the region that contains those solutions. Keep in mind, if my distance is less than some number k, then I'm going to be shading the region between my endpoints because I have a smaller distance than exactly k units. If my absolute value is greater than or greater than equal to k, then I'm going to shade on the outside of my dividing points because I'm talking about my distance being further away than those points. And don't forget that shading a number line can be a really helpful tool in answering these questions. And we will use open circles for greater than or less than, and that's the same as using parentheses when we write our solution intervals. On the other hand, we'll use a closed circle on the number line if our absolute value inequality is less than or equal to or greater than or equal to include those endpoints in our solution. We'll also use brackets when we write our solution and intervals. So here's how this goes. My first step here is going to be to isolate the absolute value expression. So I'm going to add 8 to both sides of this inequality. When I do this, I get that the absolute value of 2x minus 1 is greater than +3. You don't want to jump to conclusions and say there's no solution because of this -5 here, because we haven't isolated the absolute value yet, so we can't determine that it's actually going to be a negative number. And in fact, it's not. It's +3. So now I'm going to find the dividing points. I'm going to solve two equations. I'm going to solve one equation to see what would make this absolute value equal exactly 3. I would have the absolute value of -3 is equal to 3, or the absolute value of +3 is equal to 3. So my two equations are 2x minus 1 equals -3, or 2x minus 1 equals +3. When I solve these equations, these are the numbers that are going to divide my number line into my solution regions. So solving, I add 1 to both sides of the equal sign in both equations. On the left, I get 2x is equal to -2. See? And on the right, I get 2x is equal to 4. If I divide both sides by 2 on both equations, my dividing points are -1 or +2. Now I'm going to graph those dividing points on a number line. You never have to label these with all of the numbers in between them. We're just going to put our two dividing points, but you do need to make sure that the smaller one is on the left and the larger one is on the right. Now I'm going to use my interpretation of the distance to figure out where to shade on this number line. Actually, I'm also going to add open circles here because I know that they're not included in my answer. So what I'm thinking about is this. The distance is more than 3. And when I say the distance, I mean the distance from the midpoint between these 2 points is more than 3. That means I'm shading on the outside here. And my solution inequalities are going to be x is less than -1 or x is greater than 2. And as an interval, we get the inequality, or we get the intervals -infinity all the way up to -1, combined with the interval from +2 up to +infinity. And I have another example here, and you can see there's some help text. I'll get to that in just a moment. I'm going to follow those same steps in order to solve for x. I'm going to isolate the inequality by subtracting 8 from both sides of the equal sign. This gives me negative absolute value of 7 minus x is greater than or equal to -13. Now I'm going to divide every term by -1. I like to go ahead and show that I'm also dividing my inequality symbol by -1 as well. That's because I need to remember that whenever I divide or multiply both sides of the inequality by a negative number, I reverse the direction of the inequality. That's because if I were to look at a number line and I have, here's 0, and I have 2 numbers, say A and B, and we say that A is less than B, that means A is closer to 0 than B is. When I look at negative A and negative B, though, notice that their position with respect to 0 has changed. Negative A is greater than negative B because it's closer to 0, but a negative number closer to 0 is actually a larger value. So when I divide both sides by a negative number, I am reversing the side of the number line that I'm talking about, and I'm reversing the relationship between those numbers. So on the left side, I get absolute value of 7 minus x is greater than or no, excuse me, is less than or equal to, because I've reversed the direction of my inequality. Let me write that in pink. +13. So I'm going to solve for my dividing points. That's going to tell me that I get 2 equations. In the first equation, I'm looking at what's inside the absolute value bar, could be equal to -13. Or on the right side, I get absolute value of +13 could equal 13. So that tells us that 7 minus x could equal +13. So I'm going to go ahead and solve these 2 equations. See, I'm going to subtract 7 from both sides of the equal sign in both equations, giving me negative x equals -20, or negative x is equal to 6. When I divide both of those sides by a -1, this tells me that x could be equal to 20 or x could be equal to 6. Those are the two, or -6. Those are the 2 numbers where my distance is exactly 13 units from the midpoint. So I'm going to plot those on a number line. Always put the smaller value on the left, -6 and 20. I'm going to use closed circles on my number line because my inequality symbol is or equal to. And then I'm going to figure out where to shade by interpreting the absolute value equation. This absolute value equation tells us that the distance is less than 13 units. And when I say less than 13 units, I mean less than 13 units from the center of these 2 points. So at -6 and 20, we're exactly 13 units away. I want to shade the number line for all of the distances that are less than 13 units away. So I'll shade between those 2 endpoints. My solution interval then is going to be the interval from -6 to +20. And we'll use brackets instead of parentheses because we also can include the equal points where the distance is exactly equal to 13 in our solutions. I have 2 more examples and then we'll be all done for tonight. Let's go ahead and solve this inequality using the techniques that we've described in the previous problem. The first thing I'm going to do is isolate the absolute value symbol or the absolute value expression. I'll subtract 9 from both sides of the equal sign, giving me negative absolute value of 2x plus 5 is greater than 4. Is this the same question? No, it's not. I just remembered a 4. Now I'm going to divide both sides by -1. I write my divide by -1 under the absolute value just so I remember to reverse the direction of the inequality. So my inequality is going to switch and it's going to become less than. So on the left, I get positive absolute value of 2x plus 5 less than -4. In this case, we have no solution. Because the absolute value is always positive and a positive number is always larger than -4. So x is equal to d and e. It does not exist. And that brings us to our last problem for the evening. I'm going to solve this using the same techniques that we've practiced before. I'm going to isolate the absolute value equation. I isolate it in the opposite order of operations, which means the first thing I undo is addition and subtraction, which would normally be my last step in the order of operations. So I'm going to add 2 to both sides of the inequality. That results in 7 times the absolute value of 2x minus 4 is greater than 14. You are not able to distribute multiplication across the absolute value bars. Instead, I have to undo multiplication with division. So I'll divide the left and the right side of this inequality by 7. On the left, I get absolute value of 2x minus 4. My inequality symbol is greater than, and on the right, I get 2. So we'll solve 2 different equations to find the dividing points. We can either have 2x minus 4 is equal to -2. That's letting us know that the absolute value of -2 is equal to 2. Or we can have the absolute value of +2 is equal to 2, in which case the equation that we get is 2x minus 4 is equal to +2. I'm now going to solve for x by adding 4 to both sides of the equal sign. In both equations. 2x is equal to +2 on the left, or 2x is equal to 6 on the right. I finish finding my dividing points by dividing every term by 3 in both equations, or by 2 in both equations. It's my ADD. I know the answer was going to be 3 on the left, and I just wrote it. So we're going to do, or on the right, and I just wrote it. 2, 2, 2, 2. This gives us x is equal to 1, or x is equal to 3. So now I'm going to plot the dividing points. Make sure to put the smaller number on the left. So 1 and 3. I'm going to add open circles to my number line because my inequality is greater than, and that is an open circle. And then I'm going to interpret my inequality. This inequality means that the distance is more than 2. So that means that if I go to the right 2 and I go to the left 2, all my answers are going to be farther away from the center than 2. So I'm shading on the outside of my number line. And that lets us know our solution is the union of the two intervals, negative infinity all the way up to 1, combined with the interval 3 up to positive infinity. I hope that you understood what we did today, and please reach out to me if you have any questions because it's really important to me that I'm able to help you guys. Hope you have a good night. I missed seeing you. Bye.